Good day to IR Awam bin Taib and IR Nikmat bin Udin. My name is Mayfern. My trade ID is AA20217. My supervisor for my final year project is TX Dr. Maslan. Today, I'm going to present about my final project with the topic of simulations of sphere-voided type in reinforced concrete slab subjected to blast load. This is the content I'm going to present today. Reinforced concrete slabs are widely used in construction, but their heavy self-weight present drawback. To address this, voided slab remove excess concrete and replace it with void formals. The residential structure typically does not consider the blast load. However, there is potential for LPG explosion in residential area, causing structural damage and injuries. Next is problem statement. Voided slab aim to mitigate issues associated with heavy weight, material consumption, and construction time of traditional RC slabs. However, an LPG explosion could occur in residential area. There are many blast incidents happen in Malaysia. Here are some examples. Hence, it is important to consider the potential impact of blast loads on residential structure. Therefore, the aim of this project is to study the behavior of sphere-voided type RC slab subjected to blast load using fine element analysis and investigate the effectiveness of this approach in detail. The objective of this study is to investigate the sphere-voided RC slab subjected to blast load using ANSYS Autodyne, and to determine the effectiveness of sphere-voided in RC slab as blast-resistant structure based on the percentage concrete reduced and arrangements of voided sphere. The scope of research including the validations of numerical investigate in ANSYS Autodyne based on 1-2030. A solid RC slab as central specimen. Subsequent parametric study will explore the impact of different arrangements and numbers of voided sphere in the RC slab. The significance of my study is to evaluate the efficiency of the sphere-voided RC slab as a structure that can withstand LPG explosion. By examining the percentage reduction in concrete and the arrangements of the voided sphere, this research will develop a more efficient design standard for the blast-resisting slab. These are the research I have studied by previous researcher, and several researchers had proved that the numerical results match well with the experimental. Thus, the numerical results are reliable, so I choose to conduct simulations to investigate the sphere-voided RC slab subjected to blast load. Next is methodology. The research is divided into two sections. First, numerical modeling of a solid RC slab using ANSYS Autodyne based on 1-2030. With an accuracy of mesh sensitivity. If validated, proceed to the next section. Otherwise, repeat the same process until get the same result as 1-2033. If validated, the second section simulate a sphere-voided RC slab using the same method as solid RC slab. In this thesis, ANSYS Autodyne and arbitrary Lagrange Euler solver are employed for numerical analysis. Before exporting the RC slab to Autodyne for blast and impact analysis, solid element identification is carried out in ANSYS Workbench. The ANSYS utilizes line bodies for steel reinforcement, and 8-node hexahedron elements are employed for solid elements. Testing coarse, medium, and fine hexahedron element is carried out. This figure shows the RC slab match with the coarse, medium, and fine hexahedron elements. The 50 mm mesh size was selected for the following simulation because it provides the highest accuracies of numerical result. In Autodyne, the initial detonation of explosive and blast wave propagations are modeled with an axial symmetry in the wedge shape. The detonation runs until the blast wave reaches 1 meter from the center, generating a field file for blast overpressure history. After validating the approach on a solid RC slab, Simulations extend to sphere-welded RC slab using the same method. This is the details of tested slab will be conducted. They have RCS1 solid slab as central specimen, RCS2, 3, and 4 sphere-welded RC slab with different support arrangement. The figure 20 shows pressure time history at gauge 1, 2, and 3 under 2 kg TNT, while figure 21 shows the blast factor occurring in the air and it is about to hit the slab. Comparison result between Wang 2013 experimental and numerical result under a 0.5 kg TNT blast loop are shown in figure 22 and 23. The numerical results are slightly different from the experiment. This is due to boundary conditions of simulations always constant, but is relaxed in the experiment. However, the differences are minor. The numerical results show radial and annular crack on the upper side on the slab, particularly in the central area. This pattern is consistent with the experimental. The slab experienced larger damage at the center. Besides, on the bottom side, the lower resistance tensions of slab induced spalling caused a crater in experiment, with simulation showing more radial and circular cracks. This successful validation of the numerical simulation results are reliable. Hence, the similar simulations are used for studying a sphere-welded RC slab under blast loop. Figure below show the damage propagations patterns on the upper, bottom, and isometric side of slab 1 under 2 kg TNT blast loop. In figure 24, the minor crack is appeared at the slab center. By 3 milliseconds, this crack expanded, and at 6 milliseconds, the crack emerged in the middle of the slab due to slab bending stress in the region. And this is the propagation for slab 2. Same as slab 1, the crack increasing from 1 millisecond to 6 milliseconds. However, the lower resistance of concrete to tension lead to the development of potential spalling crater around the outer sides of the slab at 6 milliseconds. And this is the propagation for slab 3 and slab 4. This is the comparison between each of the slab at 6 milliseconds. RCS2 show higher occurrence of crack pattern, while RCS4 show the lesser occurrence of crack pattern. This visual analysis highlights the significant impact of void arrangement on the resulting structural damage. The result of effective strength applied to the reinforcement bar is shown at below. When comparing the strain value at the bottom reinforcement bar with those at top reinforcement bar, the bottom reinforcement bar experienced higher strain. This phenomenon is because of the propagation of concrete. Concrete is strong in compression but weak in tension. The bottom part of the concrete slab is subjected to tensile force, leading to increased strain in the reinforcement bar. Next is displacement. Using 5 milliseconds as the reference point, RCS2 showed the maximum displacement at 57 mm, while RCS4 record the minimum displacement at 42 mm. The displacement of each slab at gauge 11 is lower compared to gauge 10 due to the locations of the blast. Gauge 11 is slightly farther from the blast. However, both the maximum and minimum displacement remain consistent. The maximum displacement is RCS2 and minimum displacement is RCS4. Figure 41 shows almost no displacement. This is due to the fixed fault. In conclusion, the result indicates the concrete reduction increased, slab displacement when subjected to blast load increase. Increasing concrete reduction leads to higher slab damage. For example, RCS2 showed the highest damage and displacement with an 18.47% reduction in concrete volume. Lastly, the arrangements of voided sphere will affect the slab damage pattern and displacement. RCS3 is the best arrangement for sphere-welded RC slab, nearly the same capacity as RCS1. Here are some several recommendations can guide for future study. First, can use smaller mesh size for the greater accuracy. Use higher strength concrete mix design. Add additional steel reinforcement, particularly around the voids and in the critical stress zone. Lastly is different thickness of sphere-welded RC slab. This is the reference. And that's all from me. Thank you.